Is am I audible? Nithilan and Nima?
Yes, sir, you're audible.
Okay. So I just need 5 to 10 more minutes of time and a small meeting. Okay, keep revising the topics till then. I'll come and start.
Yeah, fine, sir.
Okay. Right. Shall we proceed? So yesterday we saw what happens when light travels from rarer to denser medium. Now what is there? The reverse process is when it travels from denser to rarer medium. What is going to happen? That's it. So when the light travels from denser to rarer medium, light bends away from the normal. Right? So denser to rarer medium, light bends away from the normal. That part I'm leaving it to you. You can prove it. Right? Now we will see certain applications of refraction which are important. So when I talk about the applications that are associated with refraction, one is I can talk about refraction through a glass slab. Okay. So you know what is a glass slab, right? So glass slab is basically a rectangular prism, right? So when light is passed through a glass slab, let's say of refractive index mu. Now, so here I can add a word, rectangular glass slab. When I see the top view of a glass slab, it is going to be in the shape of a rectangle. Let's say the outside medium is rarer and the glass slab is a denser medium, and again the outside medium is going to be rarer, right? So when light is striking the first boundary, no, if this angle is going to be I, right? So when the light keeps traveling in this direction, it would have traveled in the straight line path had there been no surface. So when the light starts hitting the boundary of a rarer and a denser medium, it starts bending towards the normal. So it starts bending like this, where I can call this as the refracted ray, right? At this point, again, if I draw another normal, the refracted ray inside the denser medium will start behaving like the incident ray for the second boundary. Now, this ray would have traveled in this path had there been no boundary. But since it is traveling from denser to rarer medium, it starts bending away from the normal and it gets emerged out. So that is the reason why we call this as an emergent ray. Now, if I extend it like this, observe what is going to happen. So if I take this angle to be R, okay, and I take this angle to be R1, then this angle I'll call it as E. Okay, where E is the angle of emergence. So if I look at the lines near point A and B, I can say that at A there is one normal like this, at B there is another normal like this, and there is a refracted ray in such a way that if this angle is R and this angle is R1, then I can say R is equal to R1 because they are alternate interior angles. Right? So can I take it to be alternate interior angles? Yes. So if I take the outside medium to be having a refractive index of mu1 and glass slab of refractive index mu2, and again the outside medium to have the refractive index of mu1, right? Then applying Snell's law at point A is what? Mu1 sin I is equal to mu2 sin R. Let this be equation number 1. So Snell's law at point B will give you mu2 sine R1 is equal to mu1 sine E. But this I can write it as mu2 sine R also. Why is it so? Since R is equal to R1. So when I write it in this way, this will be 2. So from 1 and 2, what I can conclude is mu1 sin I is equal to mu2 sin R is equal to mu1 sin E. Can I take it like that? Now, if I take this to be A, B, and C, since A is equal to B is equal to C, I can say A is equal to C. So mu1 into sin I is equal to mu1 into sin E. So mu1 and mu1 will get cancelled, which implies sin I is equal to sin E, which also implies I will be equal to E. So when I is equal to E, we can conclude that the angle of incidence is obviously equal to the angle of emergence. So from that, what I can diagrammatically observe is the incident ray is parallel to the emergent ray. So from this, an important conclusion that we can draw is incident ray and emergent ray are parallel to each other. Okay. So when they are parallel to each other, what happens is there is a small shift that is taking place, right? The shift that is taking place in the actual path of the incident ray is what is called as delta x, where delta x can be called as lateral displacement. Okay. So what is lateral displacement? It is the shift that has been taken place with respect to the incident ray. Or to put it in simple terms, it is the distance between incident ray and correct. It is the distance between the incident ray and the emergent ray. That's it. Is that point clear? Is it clear? Did you copy it? Good done? Okay. This is one of the applications where now we are interested to calculate what is the lateral displacement that has taken place. Is it right? So shall we try and see? Just give me a minute. I'm recording this. So the next topic that we are going to discuss is so now we will see the concept of lateral displacement. Okay. Now, as we saw in the previous concept, we understood that the light ray, which is incident on a glass slab, is getting refracted in such a way that the emergent ray will be parallel to the incident ray. So having said this, our job is to find through what distance has the incident ray got shifted for it to become the emergent ray, and that distance or shift is what we call it as lateral displacement. So if I take this angle to be I, the ray goes like this, and the emergent ray is in this format. So if I extend it in this direction, this is R, this is also R, and this is the emergent ray. And this distance is what we call it as delta X. So if I take this as A and the extended normal meeting the second refracting surface as B, and if I take this as C and this as E, the logic here is, the idea that I would like to share here is, in ray optics chapter, wherever you need to find the distances and angles are involved, there are two logics. Okay, one is you should always start applying Snell's law, especially in the case of refraction. Whenever you talk about the refractive indices and angles, it is Snell's law that is applicable. But in Snell's law, what happens? You apply sin I and sin R, which are trigonometric functions, and we know the fact that for trigonometry to be executed, we need right angle triangles. So start searching for right angled triangles. So these are the two logics that we need to always apply whenever angles, refractive indices, and distances are involved. So since in this scenario, our job is to find the distance, what we will do is we'll apply these two steps. For that, let me assign the thickness of the glass slab to be T. Now, if I look at the right angle triangle ABC, then I can say this is how it is going to look like. A, B, C, this angle is R, this will be T. Then I can think of a trigonometric function that relates thickness to AC. The reason why I chose AC is because if I look at the other right angle triangle that I'm able to see, it is ADC. If you observe in ABC and ADC, the common side is AC. So if I take this to be the right angle triangle, this is A, this is D, this is C. If I join it here, right? Now, what I can say is, if this angle is I, here the angle will be I because it is a vertically opposite angle. So out of I, R is gone means this angle will be I minus R. So here the angle A will take the value of I minus R, okay? And CD is delta X, right? Now from this, if I write cos R will be equal to T divided by AC. Similarly, in the other triangle, if I write sine of I minus R, that will be delta X divided by AC, right? So what I can think of is, I can do an operation of sine of I minus R divided by cos R is equal to delta X divided by AC divided by T divided by AC. AC and AC are gone, which implies it is equal to delta X divided by T. So from this, what I can say is delta X will be equal to T into sine of I minus R divided by cos R. So delta X will be equal to T into sine of I minus R. I can write it as sin I cos R minus cos I sin R, the whole divided by cos R. So when I do this, this will be equal to T into sin I minus cos I into tan R. So here the important point that you need to observe is, whenever you're deriving an equation, you should always ensure that the formula is applicable for practical purpose as well. Means when you do the same experiment practically and see, you should be in a position to substitute those values which are under your control. If you observe, in this expression, I can say T is the thickness of glass slab. So thickness of glass slab can be controlled by you because you can choose a glass slab of desired thickness. Similarly, the angle of incidence is in your control. That is, the angle of incidence is again in your control, but angle of refraction is not in your control. So if I observe this expression of delta X, I'm able to see tan R. My job is to remove the tan R. For that, what I will do is, first let me take this equation as 1. Then I will apply Snell's law at point A. When I apply Snell's law at point A, I can say this medium is of refractive index mu1, here it is mu2. So I can say mu1 into sin I will be equal to mu2 into sin R, which implies sin R will be equal to mu1 divided by mu2 times sin I. Let me take this as equation number 2. What I can do is, if I observe equation number 1, I am able to see that I need a value for tan R. That I need a value for tan R, but I have sin R in my hand. So since I have sin R, what I can do is I can think of a rectangle like this, where, correction, since I have sin R, I can think of a right angle triangle like this, where this is R, and I can say the numerator is mu1 sin I, that is the opposite side, and the denominator mu2 is going to be the hypotenuse, because we know that sine is opposite divided by hypotenuse. So if that is the case, what is going to be the value of tan R? For that, we will calculate the other side. That is going to be root of mu2 square minus mu1 square into sine square I, right? So I can say tan R is equal to mu1 sin I divided by root of mu2 square minus mu1 square sine square I, and let me call this as equation number 3. So I will take 3 and obviously substitute it 1. When I do this, I'll get delta x is equal to t into sin I minus cos I, sin I minus cos I into, in the place of tan R, I can replace it with mu1 sin I divided by root of mu2 square minus mu1 square sine square I. So when I do this, I get delta x is equal to t into, I'll take the sin I outside. So t times sin I into 1 minus cos I divided by root of mu2 square minus mu1 square sine square I. And this is going to be the final expression for the lateral displacement, where the outside medium's refractive index is mu1 and inner mediums, that is a glass slab's refractive index, will be mu2, which is the denser medium. In some scenarios, what can happen is, in some special cases, what we can think, if I say mu1 is equal to 1, that is the outside medium, the rarer medium is air itself, then what can happen is delta x is equal to t sin I into 1 minus cos I divided by root of mu square minus sine square I. This is the required expression. Just give me a minute. Okay. Editing. Clap பண்ணுவாங்க. அது மேல I would break. You know why movies they clap? சும்மா டைம் பாஸ் பண்ண தெரியாது. Apparent shift is spoken when you look at when you see from the top. Apparent is basically shift only. So this is lateral shift because it is happening parallelly. There it is happening vertically. So you cannot call it as apparent shift here. You will not see like that. No, glass slab you will see like this. You will see it laterally, you will not see it vertically. They have done an experiment with glass slab. Through the glass slab you will see. T into 1 minus 1 minus 1 by 2, you will get it. You would have got Ti into that is when the angle of incidence is small. Because when the angle of incidence is small, sin I can be approximated to I. Again, recheck it, it should be Ti into 1 minus 1 by mu. There will be an I outside. You have it in front of your eyes. See, T sin I replace it as I. 1 minus, when angle is small, sin I is approximated to I, but cos I is approximated to 1. Because cos is a decreasing function. So 1 divided by root of mu square minus, it will actually not be 1, it will be root of mu square minus I square. I is there. Check the formula again. T into 1 minus 1 by mu is apparent shift. Actually, that's called apparent shift. because you'll be calculating as real depth and apparent depth. The distance between the real depth and the apparent depth is called as apparent shoot. It need not be water, it can be any liquid. So just make a note of it. Scene number they'll have a book and scene number parts to match when an editor will go mad. Scene number takes the photo. Take 1, take 2, because whichever take one or piece on another, they will take that. Take 2 or piece of another, they will take that. You're giving a hint to the editor. The time pass number of us. Then he started thinking. Why will you think? So from which slide you want to copy? Here? I don't know. Is it right? Or it went too much? It's pretty slow here. This derivation very less power in the derivation. What are derivations? Snell's law where my derivation applications is. See, when it was 70 marks paper, no. This chapter and wave optics put together, out of 70, they carry 17 marks, 17. The weightage of this chapter and wave optics is 17. See, generally physics paper is set in such a way that out of 70, 55 to 53 marks will be theory. The theory might include definitions or derivations or any other theory related to the application part. And 15 to 17 is the outer limit for problems. And generally, if you see, I'm talking about the paper when it was 70 marks. Okay, 2020 exam didn't happen. I'm not sure. Last year it was only 35 marks. But before that, in 2019-20 batch, there were 4 sections. Section C were the ones where there were many problems. So what I suggest generally is when you attempt CBSE paper, go in reverse. 1 marks will be the toughest. So initially, if you see 1 mark, you will have a little bit of confusion. Especially if it is MCQ, you will definitely have confusion because you are starting fresh. Whereas 5 marks, they will directly ask you a derivation and a problem based on it. So 5 marks will not be a direct 5 marks. It will either be 3-2 or 3-1. 3 marks will be a derivation and 1 mark and 1 mark will be a problem or something. 5 more direct 5 marks. It is only 3. Okay, and if you see, the real worth is only 3 marks. Because in physics, it is more. Many people get scared because they don't get the logic. And if you see, there is a lot of mathematics that is getting involved. And why I told you they will not ask you this derivation mostly is because the physics paper is attempted by many non-math students also. They will really struggle to touch all these things. Another, they will not ask, but I should not tell that, but since you guys are already doing it, be prepared for the worst. So, let's not assume. My test, I'll ask. Another, be prepared. You will have internal choice. That depends on how the pattern is being set. With see, it's not like section C. Let's say there are 10 questions. Generally, we 8 questions, I think. I forgot, but it used to be 8 to 7, somewhere around that. Out of 8, 2 or 3 questions will have internal results. It is not like every question has an internal result. That is only for state board. So for you, the pattern is. I'm not sure of this year. Because that is what I had a meeting in school today. That's what we were discussing. Every year they change. 2017 they change, 18 they change, 19. The toughest part is setting question paper is getting tough for me. My life was happy. I used to take previous year paper and ask them to write this. Random or paper. You not even know which paper I did. Now my life is so tough. I could have so many questions. But then I MCQ paper is I ask assertion, reason based, source based questions. So that is the toughest. Even if you see competitive exam also, they are changing every year. Maybe that is where you are asking. Out of 30 questions, you need to write 25. That's not the way it is. For CPSC, it's not. See, competitive exam, at least it makes sense, especially like exam schedule, it makes sense. But otherwise, I'm not in favor of that. Choice slightly be. Your mind will start neglecting certain points. That is the danger. Yeah. So are you done writing this? So shall we proceed with the next one? Okay. So the next concept is real and apparent depth. Let us say there is a container which has some liquid in it. Right. Let's say there is a luminous object which is placed at the bottom of the container, and we will say that the object is lying at a depth of h, where this h is called as real depth. Now, a point to be noted here is we use 2 words to measure the distances vertically. One is called as altitude, and the second is called as depth. So you use the word altitude when the reference point is taken as the bottom. So anything above the horizontal level is called as altitude. Anything below the horizontal level is called as depth. So if you observe, here the distance is measured with respect to the surface, which is actually separating the liquid and the outside medium. So for time being, I'm assuming that the outside medium is air medium. Right. Now let's say you have your eye placed here. Means you're trying to look at the luminous object exactly from the top of it in the perpendicular direction. When you do this, you need to locate the position of the image formed for that luminous object. For that, we need a minimum of 2 rays. So where I'll consider one of the rays to be perpendicular to the surface. I repeat, where I consider one of the rays to be perpendicular to the boundary. So when it is perpendicular to the boundary, we know that the angle of incidence is 0 degrees. Hence, the angle of refraction is also 0. Means it is not going to get deviated at all. This is one of the rays. Right? If I take the second ray slightly inclined in this manner, and if I say the ray is incident at an angle I with respect to the normal drawn at the boundary, then what will happen? Since it is traveling from rarer to denser, it starts bending. Correction. Since it travels from, uh, since it is traveling from denser to rarer medium, it starts bending away from the normal. So when it starts bending away from the normal, we can see that both the refracted rays are getting diverged away from each other. We know that diverged rays cannot meet in real time. So you need to extend it backwards, and this is the position where you can see the image is formed. And if you try to measure the depth from the top to the point I, let me call that as H dash, and this H dash is what is called as apparent depth. So why we call it as apparent depth is because it is not the actual position at which the object is present, but it is because of the illusion we are feeling that the object has got shifted to the top. Now our job is to derive the relation between H dash, H and the refractive index of the medium. So as I told you, the outside medium is air, hence its refractive index is going to be 1. Let me say that this angle is R. Now if I apply Snell's law at point A, then I can say mu into sin I is equal to 1 into sin R. Having said this, one important point that I would like to mention here is the first refracted ray and the second refracted ray are supposed to be so close to each other because it is the eye who is looking at the image that is getting formed. So it is important that the first refracted ray and the second refracted ray, first and second refracted rays are supposed to be very close to each other, because the size of eye's pupil is very small, and it is important that they enter the eye for the person to visualize the object, for the person to visualize the image formed. For the person to visualize the image formed. Now, having said this, if this angle is R, then I can say this angle is also R because they form the corresponding angles. Okay. Now, if I take this as AOI, I'll take this point as B. So I'm repeating it, AOI and B. As I mentioned in the previous case, wherever distances are getting involved, the first thing is you need to apply Snell's law. We have already done it. And second is look for right angle triangles. Oh, I made a mistake, sorry. It is not R, it is I. It is I. Yeah, it is I. So correction is. Correction. So if this angle is R, this angle will also be R because they are corresponding angles. Whereas if this angle is I, then this angle will be I because they are alternate interior angles. So again, the logic is same. Wherever you need to find the distances, you need to go with the Snell's law and right-angled triangle. If I take this as equation number 1, since I told that the rays are closer to each other, from the above statement, I can conclude that angles are very small. The angles involved are very small. When the angles involved are small, I can say mu1 into sin I can be approximated to I will be equal to, or it is mu into sin I. Mu into sin I can be approximated to 1 into sin R. Right? Let me call this as equation number 2. Now let me look for the two right angle triangles. When I take the right angle triangles, for that, let me label it A, O, I, and B. So if I take the right angle triangle ABI, if I take the right angle triangle ABI, then this angle is R and this is H dash. So I can think of tan here. So where I can say tan R will be equal to AB divided by H dash. So I'll call it as equation number 3. Okay, tan R is AB divided by H dash. Similarly, if I take the triangle ABO, if I take the triangle ABO, okay, then this angle is I and this height is H. Then what can I say tan I is? It is AB divided by H. Let me call this as 4. But since angles involved are very small, sin I can be approximated to tan I can be approximated. Similarly, sin R can be approximated to tan R can be approximated to R. Similarly, sin I and tan I can be approximated to I itself. When that is the scenario, equation 3 will become R is equal to AB divided by H dash, and equation 4 will become I is equal to AB divided by H. Now I will take these two and substitute in 2. So if you observe, the second one is mu into I is AB divided by H is equal to 1 into R, that is AB divided by H dash. So AB and AB are gone, which implies H dash will be equal to H divided by mu, or apparent depth will be equal to real depth divided by the refractive index. So from this, what can I say the shift is? Shift is H minus H dash, that is equal to H minus H divided by mu, which will be equal to H into 1 minus 1 divided by mu. H is the real depth. Yeah, it is thickness. It is thickness. Where H is called as the real depth, mu is called as the refractive index of the medium in which the luminous object is placed. Those who are online, I hope you're able to understand. Or slightly down. So let's try to create the reverse scenario of this. That is, we will try to calculate the apparent height and see what happens. So we'll try to calculate the apparent height and see. Okay. Suppose I have a scenario where there is an object kept in the rarer medium. So where is it kept? It is kept in the rarer medium. And your eye is in the denser medium. Suppose this ray is traveling in this way, where there is a boundary. Okay. And the ray is traveling from rarer to denser. It starts bending towards the north. But still, if you observe, they are getting diverged only. There is no possibility for them to meet. So if that is the case, if I retrace it, then I'll get the image to be formed below the real height. Right. Let's try to calculate what that value. So let's say the refractive index of denser medium is mu, and the refractive index of rarer medium, I'm taking it as air for the time being, and let me call it as 1. Is that clear? So can you try out what would be the value and tell me? H and H dash. This height is H. This is H dash. Nothing. However, there is nothing wherever you keep your ray, because these two rays are never going to meet. It should be the Ravens. The Ravens. So that's the logic, because refractive index is greater than 1 always. H dash is greater than H. So it should be few times multiples of H. That is the mu H is the right answer. But see if you are getting using the derivation. task, you have to do it. But they given as a problem, you have to do it. Instead of asking, say, derive this, they will give it as a problem. This is the scenario. You can, but this concept is not there in textbook. You have only for the previous one. So previous one, yes, you can use it as a formula, but not for this one. This is I, this is R. Got it? So you understood the method? So it's very simple. By now you should have understood one thing. Wherever distances are involved, I do only three things. Snell's law and right angle triangle. That's what I said. Number of unknowns is equal to the number of right angle triangles. Is the point clear to everyone? Those who are online, are you able to understand?
Yes.
So these are the two applications we saw actually, right? So I can call it as A and B. This part I can call it as A and B because it's the same concept. So the next part that we are supposed to see is what happens for refraction at spherical surfaces. So for spherical surfaces, so whatever we saw here is with respect to the planar boundary. Sometimes it can happen with spherical surfaces. From that only we will derive two important formulae called as lens formula and lens maker's formula. Okay. After that you have the power of lens, then you have prism, followed by optical instruments. After that, we'll do some good number of problems with this chapter because it is important. So till here, is it clear? So we'll stop with this. Okay. Next class, I'll start with refraction at spherical surfaces. Okay. We'll wind up, guys.
Thanks. Bye.
Yeah.